Welcome to this explainer. Today, we're jumping straight into one of the most stubborn, massive mysteries in the entire history of physics. What actually is light? For over a century, light has been caught in this intense tug-of-war between classical physics and quantum mechanics. But there's a recent breakthrough paper in the Annals of Physics by researcher Dheeraj Sinha, and it proposes a stunning, back-to-basics solution to finally reconcile this divide. So let's explore how an old, familiar rule of classical electromagnetism might just hold the absolute secret to quantum light.
To really grasp the scale of this mystery, you have to realize it haunted Albert Einstein himself. Einstein literally won a Nobel Prize for his work on photons, the whole idea that light travels in these tiny, discrete packets of energy. And yet, in a 1951 letter near the very end of his life, he admitted, "All the 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta?" Think about that. Even the father of the photon wasn't fully convinced by the accepted narrative.
Section 1. The classical versus quantum divide. Let's get into it.
Okay, let's dive into this divide. We're looking at two historically incompatible views of light. Over on the left, we've got the classical wave theory, championed by James Clerk Maxwell. In the classical world, light is a continuous wave, and its energy is tied to its intensity. Specifically, the energy is proportional to the square of the amplitude of the electric field. Makes sense, right? But then, on the right side, we hit a massive wall with the photoelectric effect, which was first observed by Philip Leonard. When you shine light on metal and it knocks electrons loose, the energy of those emitted electrons isn't based on the wave's amplitude at all. No, it's strictly proportional to the frequency of the radiation. This bizarre observation is what forced Einstein to propose his quantum particle theory, arguing that light must actually be made up of quantized packets of energy. And for decades, these two ideas absolutely did not play nicely together.
Let's trace how this unfolded. Max Planck kicked things off back in 1901 with his idea of quantized atomic oscillators. Then, in 1905, Einstein used that for his heuristic photon theory. But guys, it wasn't an overnight success. Far from it. As science historian Bruce Wheaton noted, from 1913 all the way to 1923, there was simply no convincing explanation for the photoelectric effect using classical terms. By the end of that decade, the physics community only reluctantly accepted the light quantum to relieve what Wheaton called an intolerable state of affairs. It was basically a patch, not a perfect solution. And that brings us to 2024 and Dheeraj Sinha's bold attempt to finally reconcile this using classical electromagnetism.
Moving on to Section 2, Faraday's law holds the key.
So, the unlikely hero of our story turns out to be Faraday's law of electromagnetic induction. This is a fundamental, strictly classical law that dictates exactly how a time-varying magnetic field interacts with an electric circuit. We're not talking about some abstract quantum theory here. This is the exact same tried-and-true physical law that powers the modern solar cells and electromagnetic generators we use literally every single day. Sinha realized that the fundamental mechanism of coupling energy from light into electrons could be derived simply by going back to this deeply classical law.
So the crucial point is exactly how Sinha applied Faraday's law. Looking at his core approach, he focused heavily on the quantized nature of magnetic flux. That's the idea that magnetic fields can actually exist in discrete, measurable chunks. Now, magnetic flux quantization was discovered back in the 1960s, but scientists usually confined it to niche areas like superconducting loops. Sinha brought it front and center. He used pure classical electromagnetism to derive how energy couples into electrons. His brilliant argument here is that the energy of an electron can be discrete, and when we measure those discrete energy levels, it simply gives the appearance of the particle-like nature of light.
Section 3. Bridging the mathematical gap. Let's look at the math.
Let's move to the math and see how this builds, because this is the absolute core of Sinha's solution. Step 1 starts right with Faraday's law. Sinha shows that the energy of an electron situated in a field of time-varying magnetic flux, which is mathematically written as the derivative d phi over dt, is simply the electron's charge, E, multiplied by that flux. That is pure classical electromagnetism. Then, in step 2, he takes that classical time-varying expression and translates it into the frequency or phasor domain. This is a very common mathematical trick engineers use to simplify time-varying signals by looking at their frequency representation. When he translates it, the expression becomes EJW. Finally, step 3 reveals the monumental equivalence. Sinha mathematically proves that this classical, derived phasor expression of EJW is perfectly identical to Einstein's famous concept of light quanta, h bar w. It's mind-blowing. By merely taking a time-varying magnetic flux and translating it into the phasor domain, he elegantly derived the exact energy of a photon without ever leaving classical physics.
This represents a massive fundamental shift in our comprehension of light. Sinha is basically telling us that deriving quantum mechanical results strictly from classical assumptions, which was generally thought to be impossible because the fundamental frameworks are so radically different, is actually totally possible here. The particle-like photon isn't breaking classical rules. Instead, the concept of photons emerges as a completely natural consequence of magnetic flux quantization acting within the framework of classical electromagnetism. It means light doesn't have to be a paradox anymore.
Section 4, Reimagining the Physics Universe, and the expert reactions to this are wild.
We have some incredibly validating feedback on this paper, starting with Lawrence Horowitz, an emeritus professor of physics at the University of Tel Aviv. He calls Sinha's article a valuable contribution and an important complement, specifically highlighting its focus on the classical aspects of the theory of photons and electrons. This is huge because it grounds Sinha's mathematical derivations right in solid, expert consensus. It's not just fringe theory.
We also have this fascinating insight from Stephen Verrall from the University of Wisconsin-La Crosse. He points out that Sinha is providing a brand new semi-classical approach to modeling quantum systems. And what's really exciting about this is Verrall's prediction that this unique framework will ultimately add valuable insights into the continued development of semi-classical effective field theories. So this isn't just a fun historical correction, it's a legitimate new tool for the future of low-energy physics research.
And this brilliantly illustrates the massive historical implications of Sinha's paper. This next quote comes from a leading physicist at the University of Bristol in a personal note to the author. They note that Einstein taught us Maxwell's equations were already relativistic, like 40 years before relativity was even formalized. And now, thanks to Sinha using flux quantization to derive quantum mechanics, we realize Maxwell's classical equations were already quantum 60 years before quantum mechanics even existed. I mean, I find that absolutely amazing.
Which brings us to a really provocative question to wrap up our explainer today. By using Faraday's classical law to unlock Einstein's photon, Dhiraj Sinha has proven that the old rules of physics still have massive secrets left to reveal. If Maxwell's classical equations were already quantum 60 years before the quantum revolution, we really have to ask what else is hiding in plain sight within classical physics. It makes you wonder what other intolerable mysteries might be solved just by going back to the basics. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll see you next time.